is defined by expectation of exponential t is just a parameter, which can be calculated for discrete case and continuous case. Just like we find the expectation of random variable. This one is known as the moment generating function because the moment of x, this moment of x can be calculated by here n from 1, 2, 3, and so on. That means all this moment can be given by this formula. In the previous lecture, we have spent a lot of time to find, for example, expectation of x and the variance of x. The variance of x is just given by expectation of x square minus square of expectation. Actually, if we know the nth moment, it is very easy to calculate this one. Okay, this is the reason why such function is known as moment generating function. Okay, I will show you an example how to calculate the moment generating function. If we obtain the moment generating function just by differentiate the moment generating function phi of t this time with respect to t and evaluate the t equals 0, it is very easy to find this moment. For example, x follows in this case binomial two-parameter p. The moment generating function is given by here a from 0 to n and e t k by n choice k t k 1 minus t n minus k. This gives k from 0 to n choice k t k power ts 1 minus t n k minus k. This just use binomial formula. This gives p e t plus 1 minus t nth power. This just equals p e t minus 1 plus 1. Yes. Okay. We recall that to find the expectation of binomial and the variance of binomial is not easy. But use the moment generating function. Differentiate this one with respect to t, we find, and Yes. Differentiate T, nothing changed. Nothing changed. Evaluated at 0, NP, yes. Just evaluate. Okay. Very easy to find the expectation. It just equals the expectation. And the take derivative 2 times gives this n by n minus 1 p differentiate nothing changed. Okay. Evaluated at t here n by n minus 1, this just equals p squared plus np. Yes. And the variance of x just equals square. This just equals expectation of x square. So minus is 1. And this just equals n square p square minus np, yes, np square plus np minus np square. Okay? answer just equals NP1 minus. I show you that it is very, if we have found the moment generating function, then to find the expectation variance and the minimum very easy. Just so we can make comparison between integration and differentiation. Of course, take derivative of phi of t is more easy, simple than integration. Okay. Next example. If x follows Poisson, if x follows Poisson, determine lambda, then phi of t, just by definition, in this case, k can take from 0 to infinity, and k factorial lambda k okay. Yes. Just equals 1 minus k. Here, k from 0 to infinity. K factorial lambda t's k's power. This part. Just equals e minus lambda e lambda e t. Just equals e lambda okay. To find the expectation and the variance expectation of then phi derivative at 0 just equals take derivative with respect to t take derivative how to find such derivative? This one itself, then this one just lambda 1 and 0, 0, just equals. Okay. Just because expectation. The second derivative is 0. This part just equals e lambda et minus 1 lambda et square plus e lambda et minus 1. Take derivative, nothing changed. Okay. Evaluate t0. This 1 lambda square plus lambda, yes. The variance of x, let's say expectation of minus okay, actually you will find that use this method. It is very easy. I mean, comparison with the previous, just by definition of variance, step by step. We need a long procedure to find the expectation of variance. Okay. Next one. If x follows exponential distribution with parameter lambda, then the density function of x is given by lambda minus lambda x. Okay. Let's find the moment generating function. Up to now we have discussed the moment generating function for discrete case. This one is for continuous case, namely phi of t integrating from 0 to plus infinity lambda lambda x, yes. Tx dx just equals lambda 0 infinity e now t minus lambda x dx. This is lambda over t minus lambda infinity here, of course, we request for convergence of this one, we require that absolute value t minus lambda less than 0. Otherwise, we cannot not find prime function of this iteration. So this just equals lambda t minus lambda infinity here less than 0, minus 1. Just gives lambda over lambda minus. Okay? Can you follow me? Why we should use such assumption? Otherwise, we cannot find that to say does not exist the moment generation function if this relation doesn't hold. So in this case, t minus 1 by lambda just equals 1 equals 0. Okay. To find the variance just equals lambda t minus t whole power minus lambda by 2 okay, square minus, yes, evaluated t equals 0 just equals the variance of x just being Very easy. Next one. If X follows normal distribution with two parameters mu and sigma squared, phi of t just equals density function equal 1 over this one sigma exponential minus 2 squared and x minus mu squared and xt means here minus xt 2 sigma squared. Okay. Our question is how to simplify such part. How to simplify it? We just use this part here, this part, and exponential minus x minus 2 mu x minus 2 mu squared tx and plus mu squared. This just equals minus 2 mu plus sigma squared x. This part. Mu t's. Yes. Here we need a t. And then here here square, yes. X minus, we can write 2 mu plus sigma square t x and plus mu sigma square t square plus minus, yes. Plus term, minus term, and plus mu square. Okay. Minus. This just equals here x minus mu plus sigma square t square. No. Here you just need simplify here, namely mu plus sigma square t. Add the term minus term. Here we need to square. Plus mu square just equals yes, minus mu square minus square minus 2 mu sigma t. Yes. Plus answer this gives sigma square t minus sigma square t. Sigma square t minus 2. Okay. Step by step. this just equals here we have exponential. This part is not related to x. So minus 2 sigma square here sigma square t interchange two parts. To find the moment generation function is not so easy. So exponential yes sigma square t and sigma square t minus 2 mu by this part 1 over sigma exponential what is this? What is this? What is this? This is just a density function of normal distribution with mu or expectation and the variance this line. So density function integral from minus infinity to plus infinity just equals what? Okay, can you follow me? Any question? No question? Okay. Okay. So this just equals exponential here. This just equals constant yes, constant okay. Okay, some sign here should be plus. Something wrong here? Just step by step. Yes, plus minus. Mu 3. This just equals what's wrong with this? Here should be plus, but here become minus. Just consider it. Yeah. Minus okay, something here. Here we definitely minus. So minus here. Here should be minus. Minus, yes. Minus. Yes. Okay. Great. Okay, here should be a minus. So finally, we find that the moment generating function of Poisson of exponential is just like this one. In our class quiz, I asked you to find the expectation and the variance of a normal distribution. I think that question is most difficult for you. But if we know the moment generating function, this question becomes easy. I will show you how to use the moment generating function of normal distribution to find the expectation and the variance. Take derivative of this one, moment generating function with respect to t. Just equals expectation we also need t squared, yes, t squared. Our result is as a slide this way. Take derivative with respect to t. Here we only have one ts. By sigma square t plus mu. Value n t equals 0, okay, t 0, 0, 1, 0, 1. Okay, and take derivative with respect to t 2 times. This gives exponential and square and plus by sigma square. Value is equal to 0. This square plus sigma square. And then the variance of x cascades, and this cascades the second moment minus mu square. Okay, finish. There it is. Can you follow me? In the following, you should derive the moment generating function and by itself, and remember it. In a lot of questions, you can use the moment generating function directly, and then the question becomes easy. Okay. After consideration of several important moment generating function of several important distribution, let's consider the important properties of moment generating function. The first one. The moment of the sum of independent random variable is just a product of individual moment generating function. That to say, if x and y are independent, the moment generating function of z is denoted by this one. Expectation of in our case, x and y are independent. In such case, we use the property of expectation for independent random variables, just equals expectation of by expectation of just equals that is to say, if two random variables are independent, then the moment generating function of some of them just the product of each moment generating function. Okay. Another property, I just state the meaning of this theorem and do not prove it because prove it is out of range of our lecture. In middle class or high class, we need to prove such a theorem. That is, moment generating function uniquely determines the distribution. That is, there exists one-to-one correspondence between moment generating function and the distribution function of random variable. Keyword is one-to-one correspondence. So using these two important properties, we can previously we have several interesting and useful results. Namely, if x follows from A, y also follows from A, and then x plus y follows binomial 2t. Special case, actually, this is the first case. The second case. If x also need x and y are independent. The second thing, x follows binomial. And x and y independent. Then we conclude that x plus y also follows binomial with new parameter. This one. We have discussed this property previously. We have proved it. Do you remember? First one, second one. And the third one. If x follows Poisson with parameter lambda 1, and y also follows Poisson with lambda 2, x and y are independent. This is known as an additive property of discrete and continuous random variable. Actually, use moment generating function, it is very easy to show this. We recall that moment generating function for the first case, moment generating function of x just equals special case of binomial 1p. So binomial moment generating function is just p t plus 1 minus t. Okay. So y t just also equals to this y. What is this? What is this? What is this? It's just binomial with parameter 2p. Okay? Because there is one-to-one correspondence between moment generating function and distribution of random variable, so we say that the sum of two Bernoulli, independent Bernoulli, is just a binomial with two parameter 2p. Okay? This one. Similarly, for this one, this is just n1 power, this is just n2 power, this just equals n1 plus n2. What is this? Bernoulli with new parameter n1 plus n2. That is to say, two independent binomial with the same peak just also follows binomial with new parameter n1 plus n2p. Okay? Very easy and directive. The third statement, we recall that phi it follows just equals next one exponential lambda et minus 1. Yes. We require that yes. For the convergency limitation. Okay. For this case, because the sum of the moment generating function just exponential lambda 1 plus lambda 2 et minus 1. What is this? We conclude that x plus y also follows Poisson's arrangement. Okay, very easy. For normal distribution, phi of xt just recall that just equals exponential mu t plus sigma square t square. Okay. And mu 1 sigma 1 phi x by 1 is then we find that the sum of them can be written by what is this? What is this? Yes, it's just a new normal distribution with parameter mu1 plus mu2 and the sigma 1 and the sigma 1 square plus sigma 2 square. Okay? use this to properly I show you the power and the similarity of these two theorems use moment generating function. Okay. Actually, we in the future learning or in probabilistic model or in signal processing or in mathematical analysis, moment generating function is a very, very powerful tools to use using computation.
Hello?
In theoretical proof.
Hello?
Okay. This
Hello?
is discrete and continuous distribution with its moment generating function. Okay. From this list, we see that here gamma distribution. We did not discuss in detail in our lecture, but from moment generating function, we see that what is the relation of exponential and gamma? If x follows exponential with parameter
Hello?
lambda
Hello,
and
bro.
y also IID
That's enough.
and xy okay. That means gamma distribution with parameter n, lambda is just n the sum of n exponential distributed random variable. Just use the example we have discussed in previously. This is just, for example, this is a system in series. Then the lifetime, both of them follows exponential. Then the lifetime of total system just follows gamma distribution. Yeah. Just wait. Sum of them. Sum of them. Not this one. Not in service. In standby. Standby. Okay. Another example, see here. Suppose moment generating function of random variable is given by this one. What is the probability that x equals 0? See here. This is a moment generating function of random variable. What kind of distribution in this case? Poisson with lambda equals 3, yes. So if because there is one-to-one correspondence between distribution, moment generating function, and the random variable, so we can write the PMF of Poisson. We can write PMF and find this one. Yes. Next one. The sum of independent binomial random variable x and y are independent binomial with parameter m and n and np and np respectively. Then what is the distribution expert? I have shown you that also follows binomial with new parameter n plus p. N plus m plus np. Okay, I will show you. Next one. The sum of Poisson random variable calculates the distribution of x plus y when x and y are independent Poisson random variable with means lambda 1, lambda 2. I have shown you that also follows Poisson with mean lambda 1 plus lambda 2. Okay. The sum of two independent normal random variable with parameter mu1 sigma 1 square, mu2 sigma 2 square respectively, then sum of them also follows normal distribution with two parameter mu1 plus mu2 and sigma 1 square plus sigma 2 square. Okay. I have proved just use the property of moment generating function and prove it very easy to use this powerful tool. It is also possible to define the joint moment generating function of two or more random variables just for joint density function or joint probability mass function. This is done as follows. For any n random variable x1 from xn, the joint moment generating function is just defined by a linear combination. Here, sequence of x is just treated as a vector. The coefficients t1, t2, and tn, some of them, linear combination of x. Then the random variable are set to multivariate normal distribution here. Something. Yes. Let's say this example. If x z1 until zn be a set of n independent standard or unit normal distribution, if for some constant aij and the mu1 until mu_v, we just define this linear system. Okay, let's find for example, x1 is defined by alpha 1 1 alpha n1 z1 plus alpha 1 2 z2. I just show you a very simple example. Yes. Then the moment generating function of x1, just by definition, is just E of t substitute in here 1 1 z1 plus alpha 1 2 z2. Because they are independent, just equals expectation of E alpha 1 1 t z1 plus expectation of E alpha 1 2 t z2 just equals moment generating functions of z1 with parameter alpha 1 1 t plus I z1 2 alpha we recall that both z1 and z2 are normally distributed or standard normal distribution mu equals 0 and sigma square equals 1. So use moment generating function just equals moment generating function just mu t plus sigma square t square. Okay, so let's just remember here. In this case, k, this just equals expectation of mu t. Mu equals alpha 1 1 t. Yes. Mu equals 0 in our case. Here is 0. Okay? Yes. Because mu is 0. Sigma here just equals 1 over 2 t square. T square means alpha 1 1 t square. Okay. That to say follows normal distribution with permanent zero because no mu, zero, and the variance is alpha 1 1 square plus alpha 1 2 square. Okay? That to say if z1 and z2 are standard normal distribution, then the linear combination of them also follows normal distribution with new parameter 0 is 0, sigma 1, sigma 2. A standard 0, 1, 0, 1. Okay, this is 0, alpha 1, 1 square plus 0, alpha 1, 2 square. Okay. We can generalize this result. Actually, use a moment generating function without complicated computation. We can get a lot of useful conclusions. Okay. We can generalize this one. If x1 equals alpha 1, 1 x z1, yes, z1 plus alpha 1, 2 z2 and plus mu1. In this case, mu1 is just a constant. Use same procedure. We can show that xi also follows normal distribution with parameter mu1 and alpha 1 square plus alpha 1 square. Of course, here z1 and z2 are standard normal distribution and they are independent. Okay, time limit. Today, let's stop here.